the beginning of the semester, we talked about dependent and independent variables, okay, or dependent and independent events. So when we talked about dependent events, we said that the outcome of one event will affect the outcome of the second event. Well, here we're talking about independent and dependent variables. So what do we mean by this? Let's say that we want to determine if a heart attack depends on how much coffee consumption you have. Then we would be doing a test to determine if these two variables are dependent or independent. If they're dependent, then the amount of coffee consumption could cause a heart attack or not cause a heart attack, okay? So you can have dependence where you're saying that something that you do is causing something not to happen. Your life expectancy, does it depend on your gender? If you're male, do you have a longer life expectancy? Or if you're female, do you have a longer life expectancy? These would be examples of dependent or of dependent variables, okay? Now, we could have it as something else where it might be completely independent. Does the number of videos that you listen to affect does the number of videos that you listen to affect your life expectancy? Okay, we would assume that those are independent variables. Okay, so let's write some of this down. So when would we test to see if two variables and right now we're only talking about two variables. So a medical researcher, right? So we talked earlier about two sets of data that show a correlation, but it's not necessarily cause and effect, right? In this case, it might be cause and effect, okay? So these are the two examples that we gave. You should think about other examples. Okay, when might we want to know when two variables are related? So we can use a chi-square test to test for this independence or dependence, okay? And it's very similar to what we did in our last lesson where we did a chi-square test for goodness of fit when we were talking about whether an expected distribution differs from the observed distribution, from the frequency distribution, okay? And we're kind of doing the same thing here. We're saying, does what we expect differ from what we observe? So the process is very, very similar, okay? So I'm going to put this in a different color because this is the big thing for this lecture. You can say you're testing for dependence or independence. And how do we do this? Well, we begin with something called a contingency table. So contingency table, you've actually seen these before. We've just never named it. And a contingency table is an N by R table. N by R, I'm sorry, R by C. So R is the number of rows. C is equal to the number of columns. And this shows the observed frequencies for two variables. Okay, so when we study distributions, we use this. So just as an example, let's say that we have our favorite way to eat ice cream. And we ask a bunch of people, and we either have a cup, a cone, a sundae. Sorry, got carried away with my sundae. A sundae, a sandwich, or some other way. So these are the different ways that you might eat ice cream. And then what we might do is we might break this up into two categories where we say, okay, well, I want to know, is this dependent on the gender? Do males or females prefer eating ice cream in different ways? So what you'll see here is you'll see the frequency of each one. And what we can say here then is 504 males prefer ice cream in a cup. Uh, 148 females prefer ice cream as a sundae. Okay, so each of these are frequencies. These are called joint frequencies, okay, because they're joining the two variables together. So the number of males who like cones are 287 males like cones. 53 males said they prefer eating their ice cream in a different way. 45 females said that they prefer eating ice cream sandwiches. So this is just, these numbers represent the frequencies. And what we did is we kind of said, okay, well, there are 88 people who prefer eating ice cream sandwiches, but 43 of them are male and 45 of them are female. So we broke this up, okay? And then what we could do is we could even add totals to this. The totals would be called the marginal frequencies. Okay, so let's write that down. So the totals, so when we say the totals, the total of each row and each column are called marginal frequencies. The frequencies in each cell, so each cell is each box. I'm using the word cell because that's how we describe it formally. These are joint frequencies, which makes sense. You're joining together two variables. So these over here that we described, these are examples of joint frequencies. Okay, so our joint frequencies here, we have 10 of them. Okay, the 504 is a joint frequency of males who prefer ice cream in cups. 43 is the joint frequency of males who prefer ice cream sandwiches. 401 is the joint frequency of females who prefer cones. And then the marginal frequencies would just be the sums. Okay, so like here, the number of people who like cups is 978. We took these two and we added them and we get 978. Okay, that would be a marginal frequency. Marginal frequency if we took the total number of people who liked cones. So we're combining all of the different frequencies in a single category. So this would be 688. So we can do that for all of these. We can also go across. We could take the total frequency for males. So we're adding all the way across, and then the total frequency for females. So we're essentially taking the frequency for each individual category. Those are the marginal frequencies. And then the joint frequencies are the frequencies combining the two variables. Okay. Okay, so just like before, okay, just like in our last lecture, in order to do chi-square test, we need expected values. So the expected frequencies, okay, so these are our observed frequencies. Which kind of already says that, but to find the expected frequency, right? So we need expected frequencies for each of these cells, right? We want the expected frequency for males who prefer cups, expected frequency for males who prefer cones. So this is the first row. This would be the first column. So 504 is the frequency, the observed frequency for row 1, column 1. Okay. 287 is the observed frequency for row 1, column 2. 53 is the observed frequency for row 1, column 5. Okay. So let's put that over here first. observed frequency for row 1, column 1. That's what that means. Row 1, column 1. Okay, this is like O, R, comma, C. So this one would be the observed frequency for row 2. That should not be an R. Row 2, column 3. And the observed frequency, we'll put it down here. Observed frequency for row 1, column 2 is 287. That's a joint frequency. The observed frequency for row 2, column 2 is 401. The observed frequency for row 1, column 5 is 53. Okay, these are all joint frequencies, but joint frequencies are observed frequencies too. Okay. Okay, so let's find the expected frequencies. The expected frequency for any cell, so row 1, column 1, would be the sum of the row, so the total for that row, times the sum of that column over the sample size. So right now, the way that we have it in this table, so we're going to create a new table with the expected frequencies. We can't do it yet because we need to figure out what the totals are. We have to find the total of each column because for a male who prefers the cup, we need to take the total for males, multiply by the total for cups, and divide by the sample size, which is the sum of all of these frequencies, right? If we add all of these together, then we get the total number of people who we asked the question of. Okay, so we have to go through and do that. So I'm going to recreate this contingency table, but I'm going to leave lots of room to calculate the expected frequency. Okay, so we have gender. We have, first of all, we have the favorite way to eat ice cream, right? So we're going to have the person's gender. We're going to leave lots of room. And this time we're going to add in a total. Okay. And then we have the different possibilities. So they could eat it in a cup. They could eat it in a cone. They can eat it as a sundae. They can eat it as a sandwich. We ran out of room. They can eat it as other. And then you can't see this A. And then here we have our total as well. Okay. Sorry about that. Okay. So we're going to fill in the observed frequencies again. You're not going to be able to read the totals if I put it there. Sorry. Have to put it here. Okay. So some of these things are things that we are filling in, and some of it is stuff that we were given. So we are given the observed frequencies, okay? We're given the 504, the 287, the 182. These are things that were given to us, okay? The 43 and the 53. Then for the females, we were given the 474. We were given the 401, the 148, the 45, and the 50. Okay, here's what we weren't given. We weren't given the totals, so we're going to calculate the totals. So the total here is just this total, is we just add all of these numbers across. So 504 plus 287 plus 182 plus 43 plus 53 is 1,069. Okay, so that was our first total. This is how we're getting these numbers on the end. We take the total of the top row. Then we take the total of the bottom row. So 474 plus 401 plus 148 plus 45 plus 50. You don't have to always write all of this. I'm writing all of it so that everybody could follow along. Okay, and what we got here is 1128. Okay, then we have to get the totals of each individual column. So again, you don't have to write all of this down. You can just put it into your calculator. But 504 plus 474 is 978. 287 plus 401 gives us 688. $182 plus 48. Sorry, 148 is equal to 340. 43 plus 45 is equal to 88. 53 plus 50 is equal to 103. And then we would add the 1,069 plus 1128, right? And we get 2,197. And you should always double check. This is a great way to double check that you did things correctly. You're going to add the totals on the bottom also. and you get 2197. So let's now calculate the expected frequencies. So I'll do that in a different color. But again, this is something that we're adding in. So how do we find the expected frequency? Well, this would be the expected frequency for row 1, column 1. Okay. And what do? We take the sum of the row. So the sum of the row is 1069. Here's the sum of the row. And we're going to multiply it by the sum of the column, which is 978. And then we divide by the sample size. So this is 1069 times 978 divided by our sample size, 2197. And that gives us 475.868. Now we can do the same thing with the next one. So now this is the expected value for row 1, column 2. So we would say that as E1, comma 2. And this one, the sum of the row is 1069 again. But now the sum of the column is 688. And again, we divide by 2197. So this here is the sample size. That's the sum of everything. If you take all of these numbers in the middle that are in black and you add them all together, we get 2197. So in this one, we get 334.762. This one is the expected value for row 1, column 3. Notice the sum of the row here for all of these is 1069 because it's all the same row. And the column is that number at the bottom, which is 340. That's this number right here, 340. And we're always dividing by the same thing. Sample size is 2197. And this gives us 165.435. Here, row 1, column 4. So now it's 1069 times 43 over 2197. This gives us 42.818. And finally, last one. So this is 1, comma 5. This is 1069 times 53 over 21, not 53, 103. Okay, times 103 over 2197. And that gives us 50.117. So notice sum of the row for all of these is the same. You're using this number here. The sum of the column is the number that you see at the bottom. So you're never actually using the observed frequencies, which makes sense. Okay, the expected frequency comes before the observed frequency. You're not using what you asked people to come up with some sort of hypothesis. Okay. This one, now our first number is a 2 because we're row 2, column 1. And in this one, the sum of the row is 1128. And now it's the 978 that stays the same from here to here, right? That's the same. We still divide by 2197. And we get 502.132. Here, again, this is row 2, column 2. And this one, it's 1128. That stays the same. But our sum column, the sum of the column is 688. And we get for this one, this did not come out. I'm just going to rewrite this number. It did not come out. I want you to be able to read it. 502.132. Okay, this one is 353.238. This one, row 2, column 3. So again, 1,128 times 340. We divide again by 2,197. This one gives us 174.565. This is row 2, column 4, 1,128 again, times 88 over 2197. This gives us 45.182. And this one, this is row 2, column 5. So this is 1,128 times 103 over 2,197. And this gives us 52.883. Okay, so these down here, these are our expected values. Okay, so how do we do the chi-square independence test? Well, it's a hypothesis test. And it's just like the hypothesis test that we did in the last lecture. There's no difference actually, except this idea that when you calculate the expected frequencies, you have these two variables. So the way that you calculate the expected frequency, you have to calculate it. Okay, so it's some extra work for you. Sometimes it'll be given to you, so you might get a contingency table that includes the expected frequencies, but sometimes it won't be, and you have to go through and you have to calculate those expected frequencies. Okay, but otherwise everything is exactly the same as the chi-square goodness of fit test, which is why we're only going to do 2 examples. So we're going to use this one, and then we're going to do one more with a contingency table and calculating the expected distribution. But you'll see that the process is exactly what we did in the 3 examples that we did in the last lecture. Okay, so how do we do it? Now, if you remember, our hypothesis tests always have the same steps, right? We verify that we do our verifications. We state our hypotheses in our claim. We specify our level of significance. We identify the rejection region. Then we find the test statistic. And finally, we determine, okay, test statistic is in the rejection region, so we reject the null hypothesis, or it's not in the rejection region, so we fail to reject the null hypothesis. And then we make a claim based upon, we make a conclusion about the claim based on whether the claim is the null hypothesis, in which case we're rejecting or failing to reject, or if it's the alternative hypothesis, in which case we're supporting or failing to support. Okay, so It's the same steps. We verify. One, that it's a random sample. And two, every expected frequency, so just like in the previous one, every expected frequency is greater than or equal to 5. Okay. Again, this is like an experiment with a multinomial experiment, right? We have multiple categories. With the sundaes, with the ice cream, we have cups, cones, sundae, sandwiches, other. So this is a multinomial experiment. N times P has to be greater than or equal to 5. Okay. Second thing, we have to state the null and alternative hypothesis. And identify the claim. So in this case, the null hypothesis is always going to be that the variables are independent. This is why we call it an independence test, because we're always testing the null hypothesis. In other words, there is no relationship. The alternative hypothesis is always the opposite. The variables are dependent. Okay. Then you're going to specify your level of significance, which again is given to you, or if you're doing the experiment on your own, it's something that you decide. And degrees of freedom. So here we have two variables, right? So our degrees of freedom includes both of them. The degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Okay? So again, R equals the number of rows. C equals the number of columns. And you just multiply them together, minus 1. Once we do that, then we have to identify our critical value. It's not an I, that's an E. So our critical value, this is a chi-square independence test. So our critical value is a chi-square. And I identified the rejection region. And this is chi-square, so we're using the chi-square distribution chart. As soon as you see that it's chi-square independence test, you're going to know to use the chi-square distribution chart. Okay. Then you're going to find the test statistic. So the test statistic here is exactly the same as the test statistic for goodness of fit test. So it's the sum of your observed frequencies minus your expected frequency squared over the expected frequency. So like I said, it's exactly the same as what we did in the last lecture. And finally, you're going to make a decision and make a conclusion about the claim. And here, when you're making a conclusion about the claim, it's yes, the variables are independent or unrelated, and or the variables are dependent or related. Okay. Okay, so let's do a chi-square test for gender and ice cream. Okay, and the way people prefer eating their ice cream. So gender and the favorite way to eat ice cream are your two variables. Let's use a level of significance of 0.01. Okay? Okay, so you already have the data. Okay, I'm not going to rewrite all of the data. We're checking for a few things. One, is it a random sample? So the answer is yes. Okay. Second thing, are all of the expected values, R comma C, are all of them greater than or equal to 5? Yes. Okay. These were, I'm going to change the colors so that you can tell. I changed the colors just so that you could tell the difference between what the question is asking and then what our answer is. Okay. So we already calculated all of the expected values. So if we go back to the previous page, every one of these expected values is greater than or equal to 5, right? We have 475.868, 334.762. All of these are greater than or equal to 5. Okay, next, we're going to state our null and our alternative hypothesis. So our null hypothesis is that the variables are independent. So we say indicate your variables. So the variables gender, and favorite way to eat ice cream, are independent. And then our alternative hypothesis is that they are dependent. And we would say that this is the claim because we're trying to determine if they're related. In most cases, it's going to be clear. It's going to specifically say in the question, so whatever it is believes that they are related, okay? But I would always, if you're not sure, always make your claim the alternative hypothesis here, okay? Because that way you can support that they're related, or you could say there's not enough evidence to say that they're related versus supporting that they're unrelated, or versus not being able to support the null hypothesis. You want to be able to say something for sure. So if you can say something for sure, then make your alternative hypothesis your claim, unless it's very clear that that's not your claim. Okay. Okay, so now we need to identify the level of significance, which we gave you as 0.01, and the degrees of freedom. So remember, our degrees of freedom is R minus 1 times C minus 1. Well, in this particular example, the number of rows was 2. The number of columns was 5. So this becomes 1 times 4, or 4. So I'm just going to rewrite this down here because we have a lot of stuff in between. The degrees of freedom is 4, okay? So you take the number of rows minus 1, the number of columns minus 1, and you multiply that together. Now we need to figure out what our critical value is and identify the rejection region. So we're going to go to the chi-square chart. We're going to look up 0.01 as our level of significance and 4 degrees of freedom. So here's 0.01. Degrees of freedom at 4 is 13.277. So here's the 4. Here's the 0.01. So we're looking at that intersection there. Okay. Again, the chi-square distribution, you're never looking for numbers within the chart like you are with the normal distribution, with the z-score chart, right? Here, you're only looking at the column and the degrees of freedom. It works very similarly to the t distribution. Okay, so it's 13.277. And then our rejection region is always the same like it was in the goodness of fit test. It's always greater than. So chi-squared would be greater than 13.277. Okay, then we have to calculate our test statistics. So we love this part. So this is the part of the hypothesis test that is extraordinarily tedious. And in this one, it's even more tedious because you might have to calculate your expected frequencies, okay? But this is just a chart. So we have 2 variables here. So first of all, we're going to have our O. We're going to have our E. We're going to have our O minus E. Our O minus E squared. And our O minus E squared over E. Okay, so how do we do this with 2 variables? Well, let's go back to that chart. So you need to make sure that one of these is in the O column, one of these is in the E column, right? And these are next to each other because this is what you're comparing, the 504 to the 475.868. Now, it makes no difference what order you go in. So you could do the 504 and the 475.868 as the first row of that table, and then 148 and 174.565 as the second row of that table. The order makes no difference. However, you don't want to forget any of these frequencies. So my suggestion is that you go across the rows. So as your observed frequencies, you would do 504, 287, 182, 43, 53. And then 474, 401, 148, 45, 50. And your expected frequencies across would have to be the same. You're going across the rows. Okay. Now remember, these totals are only there to calculate the expected frequency. They're not there for any other purpose. So these totals are not going to wind up in your tables. Okay, so what does this mean? This means 504 gets paired with 475.868. Then we had 287. The expected frequency, I'm going down the rows, was 334.762. Then we had 182. The expected frequency was 165.435. 43, 42.818. 53, 50.117. 474. 502.132. So you can see that the numbers are large again. That's because we're up to females and cups at this point. Females who prefer cups. We went back to the beginning of the second row. 401. 353.238. 158. 174.565. 45. 45.182. And finally 50. 52.883. Okay, so now we just do all of our calculations. Tedious, but not difficult. I just want you to, I'm drawing the lines because I know that things come out a little slanted here. Clearly I have a slanted mind. And I want to make sure that you could differentiate between the different calculations. Okay, so this one, remember, you're doing 504 minus the 475.868. So we get 28.132. Okay, so I'll put this in blue. We won't do this for all of them. But this number comes from doing 504 minus 475.868. And then this number comes from doing 28.122 squared. Okay. Sorry, 132 squared. So what do we get there? We get 791.409. Okay. And then this is from doing 791.409 over the expected frequency for that row, which was 475.868. Okay, that's how we calculate it. This is an 8. So there we get 1.663. And we could keep going. So I'm just going to fill in the numbers. I would suggest that at this point you pause the video and you do at least some of these by yourself so that you know how to calculate it, okay? And that way, if you're having trouble, you can send me an email or post to Blackboard and say, hey, these are the numbers I'm getting. I don't understand why I'm getting numbers that are so different from yours, okay? So this one we're getting by doing 182 minus 165.435. This is 43 minus 42.818. Then we do 401 minus 353.238. And finally, we're doing 50 minus 52.883. Okay. And then we're squaring. So when you have a negative number squared, it turns positive. If you're getting negative numbers when you've squared, it's because you're not putting the number in parentheses. Okay. So we get 2281.209, 274.399. Notice we're going to like the third decimal place. Again, we're doing negative 16.56 squared. It turns positive. Okay, now we're doing that 2281.209 and we're putting it over this 334.762. So we're taking the fourth column and we're putting it over the second column. Okay, and we get 6.814, 1.659. Some of these I'm going as far as the third decimal place, as far as the fourth decimal place. The idea is that you don't want a rounding error. You don't want it to be that you rounded too much, so your test statistic is completely off. So you're better off going further. Okay. So now we need to find the test statistic. So the test statistic, if you remember, is the sum of this very last row here, this very last column. So you don't have it in front of you now on the page, but I'm going to give it to you. So we have O minus E squared over E, and those numbers were 1.663, 6.814, 1.659, 0.0008, 0.166, 1.576, 6.458, 1.572, 0.0007, and 0.157. And when you add all of those together, you get 20.067. Okay, so then we have our last step, and our last step is to make our conclusion. So 20.067 is in the rejection region. It is greater than 13.277. That was what we found as our critical value. So it is in the rejection region. So when it's in the rejection region, we reject the null hypothesis. Okay, what does that mean? That means that the variables are related. And we say at 1% level of significance, we haven't been saying this in our conclusion before, and that's okay. Okay, you might even want to specify what the variables are. That's a good thing to do. So a lot of this is about the way that we communicate. Okay, so how are we communicating to other people our conclusion? If we are not including the whole test, okay, or even the question, so when we're not giving this information like 1% level of significance and the actual variables, the reason why we haven't been doing that is because the question is right there. If there is no question, then you have to put that in. Okay, so everything that you've been doing in this class, so for your final, for your quizzes, you are always given some sort of question. So I've never been very particular about your writing this down, but I want to be clear that when you're doing a study, okay, you need to communicate the results of that study very clearly. And there is no question. And certainly in a paper, you don't want people to have to flip back 20 pages to figure out exactly what you're doing. So in those cases, you want to be specific, 1% level of significance, and what those variables are. And keep in mind, one of the reasons why we talk about 1% level of significance is because if you look at this, if you look at the chi-square distribution, right, at 4 degrees of freedom, depending upon what your level of significance is, you have very different numbers, okay? We had 13.277, but at 10% level of significance, it's only 7.779. At 0.5% level of significance, it's 14.860. So in this case, these variables are dependent regardless of which of these numbers we use, because 20 is greater than all of those numbers. But that's not always the case, okay? So in a lot of cases, you do want to specify. But as I said, we have the question, which is why I haven't been as particular about that. Okay, let's do one more example. So we're going to do the same thing, chi-square independence test. So let's say the marketing consultant for a travel agency. wants to determine if travel concerns are related to travel purpose. So the contingency table shows the results of a random sample of 300 travelers. So we're going to use a level of significance of 0.05. We want to know if the consultant can conclude that the variables are related. Okay, so let's create this table. Okay, so first of all, you have your travel concern. So the different concerns are a hotel room, leg room on a plane, rental car size, or some other problem. Okay. The travel purpose could be either business or leisure. So this is the data that's given to you. I have it in black here because it's given. Okay, and you're given 36 people. I'm leaving room because we know that we have to calculate expected, right? This is 108 people. In other words, 108 people who are traveling for business, and leg room on the plane is their biggest concern. Okay. Rental car size is 14 and 22. Here at leisure, we say 38. We say 54, 14. So in other words, people who are going away on leisure, their biggest travel concern is rental car size. And other. Okay. Now remember, we have to calculate the totals. So sometimes those are given to us. I'm not giving it to you here because I want you to learn how to calculate it. Okay. So here, this is totals that we're figuring out. So all we're doing is we're adding the 36 plus 38. Okay, so the total here is 74. Here we're doing 108 plus 54. Total here is 162. 14 and 14 is 28. 22 and 14 is 36. Okay. Then we're adding together all of these numbers. So we're doing the 36 plus 108 plus 14 plus 22. And we get 180 here. So there are 180 people who, in the sample, 180 of them were, their travel purpose was business. Okay. Here, we add together all of the numbers and we get 120. 120 people went away for the purpose of leisure. And we know if you add them all up, you should get 300. And you do. If you add up 180 and 120, you get 300. 74 plus 162 plus 28 plus 36 is 300. Okay. Okay, now we have to do our expected frequencies. Again, this is tedious. I get it. Totally tedious, but it needs to be done. Okay. So this one would be 180 times 74 over 300. Right? So we take the row total times the column total divided by the sample size. And we get 44.4. Here we take the row total. Row total is 120. Column total is 74 over 300. And we get 29.6. Here, row total, 180. Column total in this case is 162 over 300. This gives us 97.2. Here, row total is 120. Column total, 162. We divide by 300. This gives us 64.8. Here, row total, 180. Column total, 28. Sample size, 300. We get 16.8. Here, row total, 120. Column total, 28. Sample size, 300. We get 11.2. Here, row total, 180. Column total, 36. Over 300. We get 21.6. Row total, 120. Column total, 36. Over 300. And we get 14.4. Those are our expected frequencies. Okay? Okay. Let's do our hypothesis test. Yes, it's a random sample. It says so. We calculated all of our expected frequencies. They are all greater than or equal to 5. So that's why we have to calculate those before we even start the hypothesis test, because we have to check for that. Okay. Now we're going to state our null and our alternative hypothesis. Our null hypothesis is always that the variables are independent. State your variables here. This I'm not gonna say it's okay to just say variables. You have to state your variables. So the variables, travel, purpose, and travel concern are independent. Or unrelated. Alternative hypothesis. The variables, travel purpose, and travel concern are related or are dependent. This is the claim. So most of the time this is going to be the claim, okay? Not all the time. Sometimes it'll say, can we show that they're not related? Okay, in which case the claim would be the null hypothesis. This is saying, can the consultant conclude that the variables are related? So that's why our claim is dependent, is alternative hypothesis, okay? Our level of significance is 0.05. That was given to us. Degrees of freedom, we know, is the number of rows minus 1 times the number of columns minus 1. So the number of rows here is 2. So we have 2 minus 1. The number of columns here is 4. So 1 times 3 is 3. So I'm just rewriting this down here so that it's clear, because we have all of the stuff in the middle. I'm just taking out the stuff in the middle. Okay. Now we need our critical value. So we're going to go to our chart. This is sub-0, right? That means it's a critical value. We're going to look up 0.05 significance and degrees of freedom 3. So here's 0.05 significance, degrees of freedom 3, 7.815. So our rejection region is if our chi-square, our test statistic, is greater than our 7.815. Okay, so now we get to do the fun part. We get to calculate our test statistic. So we have our observed, we have our expected, we have our observed minus our expected, we have our observed minus our expected squared, and then we're going to take our observed minus our expected squared and divide by E. Okay. This is the fun part. So I'm going to give it to you because it's on the previous page. But again, we're just going to go across the rows. So 36, 108, 14, 22, 38, 54, 14, 14. And we match up the observed with the expected. So the 44.4 has to go next to the 36. 97.2 has to go next to the 108. Okay. So we have 36, 108, 14, 22. Then in the second row, we have 38, 54, 14, and 14. And like I said before, most of the time this is done with technology where you plug in the observed and expected frequencies and it does all of the calculations for you. I want you to be able to do it by hand. I also don't expect you to have those technologies. Okay. The expected frequencies were 44.4. Again, this is just going across the rows. Expected frequency for the observed frequency of 36 was 44.4. For 108, it was 97.2. So these were in the same, the 36 and the 44.4 were in that same box where we were talking about business and hotel room, okay, as the concern. Then we have 16.8, 21.6, second row, 29.6, 64.8, 11.2, and 14.4. Then we subtract. We do our observed minus our expected. 36 minus 44.4 is negative 8.4. 10.8, negative 2.8, 0.4, 8.4, negative 10.8, 2.8. Notice when the observed is greater than the expected, it's positive. Makes sense. And negative 0.4. Then we square these. So remember, negative 8.4 has to go in parentheses, right? It's negative 8.4 squared. So we get 70.56. 116.64. 7.84. 0.16. 70.56. 116.64. 7.84 and 0.16. Okay. This is a 5. Top didn't come out. Okay. So now here we would be doing 70.56 over 44.4. So we do this third column divided by the second column. Okay. And what do we get? We get 1.5892. We get 1.2. This is exact. 0.467. 0.007. 2.384. 1.8. 0.7. And 0.011. Okay, so what does this mean? Now we add it. So we add that last column because we're talking about a sum. If we add this all together, we get 8.1582. Okay. Okay, so now we're ready for our conclusion. Well, 8.1582 is greater than 7.815. So, x squared is in, chi-squared, sorry, not x squared. Chi-squared is in the rejection region. What does this mean? This means we reject the null hypothesis. So the variables travel purpose and travel concern are dependent, and I'm going to put in at a 5% level of significance, and this is why I'm putting it in. I'm going to put a note down here. At a 1% level of significance, remember level 1% would mean if we had done this with alpha equals 0.01, chi-squared would not be in the rejection region. Which means that we would not have enough evidence or we would conclude the variables travel concern and travel purpose are unrelated. Let me show you why. So this is easy to see because our rejection region, right, our critical value, if alpha is equal to 0.01, let's go to that chi-square distribution. At 0.05, we said that our chi-square, our critical value, is 7.815. But if we go to 0.01, it's 11.345. And 11.345 is greater than 8.1582. 8.1582 would be outside the rejection region. It would be outside the rejection region if we did a 2.5% levels of significance. Okay, so this is why in your conclusion putting the level of significance can be helpful, because depending upon the level of significance, it could change our conclusion. Okay, and this would change our conclusion. At anything less than a 5% level of significance, okay, any of these three numbers, we fall outside of the rejection region, which means that we would be claiming that the variables are independent. Okay, so we want to be careful about that, and that would be the big reason for putting in the level of significance. Now like I said, we haven't, because we have the problem in front of us, so we all know what the level of significance is, but it is a good habit to assume that that problem isn't there when you write your conclusion. Okay, and that is it. Okay, that's all. This is the very last video of this semester, so thank you. And it's taking me a minute to stop it, so if you're still listening, stop listening.